Hello friends, welcome to our channel HT and LT Electrical and Electronics Engineering. Today here I am going to discuss about current transformer part 1. Let's start. Here it is brief description of current transformer part 1. The connection of an ammeter when used in conjunction with a CT for measurement of alternating current are shown in figure 1. Here it is supply, here it is load, here it is primary winding, and here it is the current transformer, secondary winding, and here it is the ammeter in figure 1. The primary winding, which consists of only one or a few turns, is connected in series with the load circuit and so carries the load current to be measured. The secondary winding consists of many more turns than the primary and connected with current coil of the instruments. Instruments such as like ammeter, wattmeter, multifunction meter in series. The current transformer in operation slightly differs from that power transformer. In case of current transformer, as the load impedance or burden on the secondary is very small, so the current transformer operates on short circuit conditions. Okay, next. Also, the current in secondary winding is not governed by the load impedance on the secondary but depends upon the current flowing in the primary winding, main circuit current. The amount of power which the current transformer handles is small. The product of the voltage and current on the secondary side when the CT is supplying the instrument with its maximum rated value of current is known as rated burden and is measured in volt amperes. The usual rating of a CT is very small, like 15 VA, and in no case exceeds 30 VA. Vector diagram of a current transformer is represented in the next figure 2. The vector diagram is not to scale. The magnitude of the magnetizing component Im and the iron loss component IE of the exciting current I0 are extended for convenience in drawing. Taking flux as reference vector, the induced EMFs in the secondary and primary winding ES and EP lagging behind the flux by 90 degree are drawn. The magnitude of the vector ES and EP are being proportional to the secondary and primary turns. The excitation current I0 has two components, Im and IE. Im is the magnetizing reactive components of no load current which creates the flux, and IE is the energy active component which supplies the hysteresis and eddy current losses in the core. Thus, secondary current IS lags behind the secondary induced EMF by an angle theta, where theta is the sum of the angle delta, the angle produced by the secondary winding resistance and reactance, and gamma, the angle produced by the burden connected to the secondary winding. In practice, for a primary CT, the reactance of secondary winding is usually negligible and delta is 0. The secondary current is now transferred to the primary side, reversing IS and multiplying by the turns KT. The resultant primary current IP is the vector sum of KTIS and no load current I0. Okay, next. Here I am introducing about the vector diagram. Here is the secondary current IS, and this is taken reverse KTIS, and here is the primary current IP, which is the resultant of KTIS and I0. IM is the magnetizing current, IE is a exciting current, where the I0 is the resultant of IE and IM. Here is the EP, primary voltage, which is shown here reversed, and Vs is the secondary voltage after the resistance and reactance drop. Vs at the secondary voltage after deducted of Is and ISRS and ISXS from ES. And here is the reference phi. Here is the flux taken as a reference vector phi. Okay, next. There are two types of errors introduced into the circuit by the CT. These are ratio error and phase angle error. Ratio error: from the vector diagram, primary current IP is equal to length OD, approximate length OC, where OC is a vector obtained by drawing the reverse secondary current vector OA and dropping perpendicular CD from the primary current vector OD. Since in practice the phase angle beta between primary and reverse secondary currents is very small, so the length of OC is very nearly equal to the length OD. Again, primary current IP is equal to length OC is equal to OA plus AB plus BC is equal to KTIS plus I0 cos alpha sin theta plus I0 sin alpha cos theta. Since IM is equal to I0 cos alpha and IE is equal to I0 sin alpha, so IP is equal to KTIS plus I0 sin theta plus alpha. If theta is very small, then primary current IP is equal to KTIS plus I0 sin alpha is equal to KTIS plus IE. This I0 sin alpha is equal to IE. Actual current ratio KC is equal to IP by IS, KT IS plus IE divided by IS is equal to KT plus IE by IS. From the above expression, we conclude that actual current ratio is equal to the turns ratio plus the energy component of the excitation current and secondary current. The ratio error is mainly due to energy component of excitation current. The ratio of energy component of excitation current and secondary current IE by IS is known as ratio error, and determines the amount of turns of compensation necessary to reduce the error to minimize. Okay, next. Here it is phase angle error. The phase angle error is introduced on account of exciting current. The angle between the primary current and reverse secondary current is known as the phase difference of the current transformer. From vector diagram, tan beta is equal to CD by OC is equal to BG plus FG divided by OA plus AB plus BC is equal to Im cos theta minus IE sin theta. KTIS plus Im sin theta plus IE cos theta is equal to Im cos theta minus IE sin theta divided by KTIS I0 sin alpha plus theta. In practice, I0 sin alpha plus theta is very small compared with KTIS and hence can be neglected, and being very small, tan beta can be taken as beta. So beta is equal to Im cos theta minus IE sin theta by KTIS. I0 cos theta cos alpha minus I0 sin theta sin alpha divided by KTIS is equal to I0 cos alpha plus theta divided by KTIS. If secondary phase angle theta is very small, then beta is equal to I0 cos alpha by KTIS is equal to Im KTIS radians. Then it is converted to multiplying by 180 by pi 2 degrees. From the above expression, it is obvious that if theta is very small, then phase angle error is mainly due to magnetizing component of excitation current. Okay, thank you for watching the video. If you think the video is useful to you, then please share it to your friends and subscribe our channel. Next we meet in the city part 2. Okay, thank you. Bye.